Imagine Mission Control, December 19th, 2025. The screens show 3i Atlas, exactly where it should be, exactly on schedule, screaming past Earth at interstellar velocities. Then someone notices the number. The velocity's dropping, not drifting, plummeting. In 6 hours, every major power knows. In 12, markets are in freefall. In 18, the term Rio Scale 10 enters the global vocabulary. Confirmed immediate contact. Here's what nobody's prepared for. We have protocols, official protocols, rules written decades ago for what humanity does if something intelligent arrives. But those rules were written for radio signals, not for objects that break into orbit. Tonight, we're examining what happens when an interstellar visitor doesn't just observe us from a distance, but chooses, deliberately, to get closer. Because if it slows down, if it stops, that choice means something. Stay with us. The implications go deeper than you think. If you're as captivated by this mystery as I am, go ahead and subscribe so you stay in the loop as new developments emerge. Leave a comment letting me know where you're watching from, what hour it is in your corner of the world, and what your thoughts are on the December 19th flyby. Part 1. It Braked. December 19th, Scenario and Breaking Claims. December 19th, 2025. The day the universe stops being theoretical. Imagine this. You're in mission control, watching a screen that's been tracking the same hyperbolic trajectory for months. Coffee's cold. Someone's complaining about the vending machine. Then a number changes. Just one number, but it's the wrong number. The velocity vector that should be climbing as 3i Atlas whips past Earth at 270 million kilometers distance. It's dropping, not drifting, not wobbling within error bars. Dropping. Fast. Your colleague notices it first. She goes quiet. The kind of quiet that makes everyone else go quiet. Someone pulls up the telemetry again, thinking it's a glitch. It's not a glitch. The object that was supposed to scream through the inner solar system and vanish forever into the void has just performed what engineers would call a high-energy retrograde burn. What the rest of us would call hitting the brakes. Hard. Within 6 hours, every major observatory on the planet is retasking. Within 12, the first unconfirmed reports leak to social media. Within 18, the conspiracy theories have already outpaced the science. By the 24-hour mark, someone in a position to know uses the phrase orbital capture in an encrypted email that immediately stops being encrypted. This is the scenario we're exploring today, not because it's happening, not because it's likely, but because if it did happen, everything you think you know about humanity's place in the cosmos would change before you finished your morning coffee, and we would have exactly 0 days to prepare because we'd already be in it. Let me be absolutely clear from the start. According to every published trajectory model, 3i Atlas is going to pass Earth at a safe distance of roughly 1.797 astronomical units on December 19th. That's about 270 million kilometers. You could fit nearly 700 Earths between us and that object. NASA's not worried. The European Space Agency is not worried. The people who track rocks for a living are treating this like any other interstellar visitor, which is to say they're excited but not panicking. But here's what's fueling the speculation that won't die. 3i Atlas isn't acting like other interstellar visitors. It's been erupting, not continuously, but in bursts, jets of material shooting out from the surface, the brightness pulsing. Some observers claim they're seeing color changes. Others report what look like ice volcanoes triggering across the surface as it moves through the warming environment closer to the sun. These aren't fringe observations. These are documented in peer-reviewed spectroscopy, in photometric surveys, in images captured by some of the most sophisticated instruments humanity has ever pointed at the sky. Most scientists will tell you this is exactly what you'd expect from an active comet made of primordial ice encountering solar radiation for potentially the first time in millions of years. Volatiles sublimating, dust getting kicked up, the whole surface waking up like a frozen lake cracking in spring. But some people are asking a different question. What if those jets aren't random? What if that pulsing isn't chaotic? What if something inside that object is controlling the outgassing, using it, steering with it? What if 3i Atlas didn't just wander into our neighborhood? What if it aimed for it? That question leads to another question, and that question leads to a phrase you've probably never heard before but which keeps some people awake at night. Rio Scale 10. It's the astronomical equivalent of DEFCON 1. It means confirmed high credibility detection of extraterrestrial intelligence with serious consequences for human society. Not a maybe. Not a We think we saw something. A check mark next to the box labelled, "We are not alone, and they're here." If 3i Atlas slows down on purpose, if it sheds enough velocity to enter a stable orbit around Earth, or even just to loiter in our cosmic backyard longer than physics says it should, that's not Rio Scale 10 immediately. That's Rio Scale 10 with a countdown timer, because the next question everyone will be asking is the one nobody wants to answer. Why did it stop? What does it want? And who's driving? The consequences of that scenario aren't academic. They're economic, societal, psychological. Markets don't handle uncertainty well. They handle existential uncertainty even worse. When people stop believing the future will look like the past, they stop investing in the future. They pull money out. They hoard resources. They panic. And in a globally interconnected economy, where confidence is the only thing holding up half the system, panic spreads faster than any virus ever could. Religious institutions would face questions they've never had to answer outside theoretical discussions. Governments would face populations demanding answers they don't have. And every single person on this planet would have to reckon with the fact that the universe is not only more populated than we thought, it's populated by something smart enough to travel between stars and curious enough or motivated enough to stop here. That's the scenario we're unpacking. Not because I'm claiming it will happen, I'm not. The physics argue strongly against it. The observational data supports natural explanations. But if we've learned anything from history, it's that the scenarios we don't prepare for are the ones that hurt us most. And right now, humanity has protocols for asteroid deflection, protocols for nuclear war, protocols for pandemics. We even have protocols for what to do if we detect a radio signal from an alien civilization. What we don't have is a protocol for what happens if the alien civilization shows up unannounced and parks in orbit. So here's what we're going to do. We're going to walk through the science. We're going to examine what we know and what we're guessing. We're going to look at the official playbook humanity drafted for exactly this kind of event, and we're going to ask the uncomfortable question of whether that playbook would actually work under pressure. Then we're going to zoom out and see how recent discoveries in astrophysics, how new technologies, how the chaotic information environment we all live in now might make this scenario more dangerous or more manageable than anyone's planned for. By the end, you're going to understand why December 19th isn't just another date on the calendar for some astronomers. You're going to understand why a single velocity change in an object millions of kilometers away could trigger a cascade that reaches your bank account, your government, your sense of what it means to be human. And you're going to understand why, even if 3i Atlas turns out to be just a comet after all, we should be very, very glad we're having this conversation now, instead of on December 20th when it's too late to matter. Part 2. Physics Triage. How physically plausible is a capture? Let's talk about what it would actually take for 3i Atlas to stop, not in science fiction terms, in Newton's terms, in cold, unforgiving physics. 3i Atlas is on what astronomers call a hyperbolic orbit. If that sounds dramatic, it is. A hyperbolic trajectory means the object is moving faster than escape velocity relative to the Sun. It's not bound to our solar system. It came from somewhere else. It's passing through, and under normal circumstances it's leaving forever. The orbit has an eccentricity greater than 1, which in orbital mechanics is the mathematical way of saying, this thing is not coming back. It's also retrograde, meaning it's moving in the opposite direction relative to the planet's orbits. Imagine traffic on a highway, everyone going the same direction, and then one car screaming past in reverse doing twice the speed limit. That's 3i Atlas. It's not just fast, it's fast in the wrong direction, which makes slowing it down even harder. So what would it take to go from that kind of trajectory to a stable orbit around Earth? Engineers measure this in something called delta V, change in velocity. It's the currency of space travel. Every maneuver costs delta V, every course correction, every orbital insertion. And for an object moving at the speeds we're talking about, on the trajectory we're talking about, the delta V required to break into Earth orbit would be enormous. We're talking kilometers per second, multiple kilometers per second. To put that in perspective, the entire Apollo program, all the launches, all the moon landings, all the returns to Earth, that was built around managing delta V budgets measured in kilometers per second. And that was with chemical rockets, with staging, with every optimization we could engineer. Now imagine an icy rock the size of a small mountain having to generate that same kind of thrust. Naturally. Because here's the thing, comets do have jets. They do release gas and dust, and that release does create thrust. When sunlight heats the surface, volatiles like water ice, carbon dioxide ice, and other frozen materials sublimate directly from solid to gas. That gas expands rapidly and shoots out, carrying dust with it. That's what creates the coma, the fuzzy cloud around the nucleus and the tail. That outgassing creates a tiny rocket effect. Scientists call it non-gravitational force, and it's real. It can slightly alter a comet's trajectory over time, but slightly is the key word. The amount of delta V you can get from natural cometary outgassing is measured in meters per second over months, not kilometers per second over hours. It's like comparing a birthday candle to a rocket engine. Technically, both produce thrust. Practically, one is not capturing you into orbit around anything. Recent spectroscopic observations of 3I Atlas show exactly what you'd expect from a naturally active comet. The coma is dominated by carbon dioxide with water vapor, carbon monoxide, and dust. James Webb Space Telescope data confirms this. Infrared observations show absorption features consistent with ices and silicate dust. This is normal. This is what comets made in the outer reaches of another star system, preserved in the deep freeze of interstellar space for millions of years, should look like when they encounter a sun for the first time in their lives. The dust production rate is high by interstellar object standards, but it's not absurdly high. It scales with heliocentric distance the way you'd expect. Closer to the sun equals more heat, equals more sublimation, equals more dust. The photometric data, the brightness measurements over time, fit models for volatile-driven activity. Not perfectly, because comets are messy, chaotic things, but well enough that nobody's writing papers titled 3I Atlas violates known physics. There's even this weird detail that actually supports the natural interpretation. Polarimetric observations, which measure how light scatters off the dust, detected something unusual. 3I Atlas shows extreme negative polarization, which is rare. Most solar system comets don't do this. Most asteroids don't either. It suggests the surface composition is different. Maybe the dust grains are different. Maybe the ice-to-rock ratio is different. And here's the thing about that. If you were designing a spacecraft, if you were building an interstellar probe, you wouldn't cover it in fluffy ice and dust that creates bizarre polarization signatures. You'd use metals, composites, materials that don't sublimate. The fact that 3I Atlas looks weird in ways consistent with exotic natural ice, rather than weird in ways consistent with artificial materials, that's actually a point in favour of it being a comet, not against it. So scientifically, with the data we have, the idea that 3I Atlas could naturally break into Earth orbit is not just unlikely, it's physically implausible, bordering on impossible. But let's Steelman the other side for a moment. Let's say we're wrong about something. There are two ways this could go sideways. Option 1, our measurements are off, way off. Maybe there's a massive ephemeris error, a miscalculation in the orbit, and the object's trajectory is actually much less hyperbolic than we think. Maybe it's barely unbound, and a small nudge could tip it into capture. This would require multiple independent observatories to have made the same systematic error, which is unlikely but not theoretically impossible. Option 2. There's a mechanism we don't know about. Some form of propulsion or energy manipulation that doesn't involve blasting gas out the back like a rocket. Maybe electromagnetic. Maybe something we don't have words for yet. This is where we leave the realm of known physics and enter speculation, and I want to be very clear about that line. We're crossing it now. We're in the territory of what if. If 3I Atlas could break, if it had some way to shed velocity that we're not detecting, that would mean one of two things. Either it's not what we think it is, or the laws of motion as we understand them need an addendum. Both options would be world-changing. One is just more immediately terrifying than the other. But here's the critical point. The absence of evidence for breaking is not the same as evidence of absence of intent. We wouldn't necessarily see the deceleration until it happened. By the time we detected a significant velocity change, the maneuver could already be underway, and that's assuming we'd even recognize it as a maneuver, rather than a measurement error or a natural perturbation. Which brings us to the question nobody wants to ask out loud, but everyone's thinking. If it did break, if the impossible happened and 3I Atlas dropped into orbit around Earth, what exactly would we do about it? Who would decide what we do about it? And how fast could we even make that decision before the entire planet dissolved into chaos? Because that's where the physics problem becomes a human problem, And human problems, as we're about to see, are a lot messier than orbital mechanics. Part 3, Legal and Scientific Playbook, First SETI Protocols, Rio Scale, and Don't Reply. Turns out, we do have a plan, sort of. Back in 1989, a group of scientists got together and asked a question that probably seemed purely academic at the time. If we detect a signal from an extraterrestrial intelligence, what do we do next? Not in the sense of how do we decode it, or what technology do we use, but in the much more mundane, much more important sense of who tells whom, and how do we keep everyone from losing their minds. The result was a document called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence. Catchy title. Most people call it the First SETI Protocols, or just the Protocols. It's been updated a few times since then, refined, debated, but the core principles remain. And if 3i Atlas performs a capture maneuver, if it makes itself known as something other than a comet, these protocols are what's supposed to happen next. Let me walk you through it, because it's both more detailed and more fragile than you'd think. Step 1. The detection. Let's say an observatory, doesn't matter which one, detects something anomalous. A velocity change, a radio signal, a geometric pattern in the object's behavior that screams intelligence. The protocol says that team doesn't immediately blast the news to the world. They confirm, they double-check their instruments, they eliminate every possible source of error, contamination, or interference. This is standard practice in science, but it's especially critical here because false alarms in this domain are career-ending and civilization-rattling. Step 2. Independent verification. Once the original team is confident they're seeing something real, they share their data with other qualified researchers, not the media, not the government yet, other scientists, people who can replicate the observation, who have access to different instruments, different methodologies. The goal is consensus, multiple independent confirmations before anyone says the word confirmed in public. This is where it gets interesting. The protocols explicitly state that researchers should treat candidate detections with provisional caution. The phrase they use is as with laboratory results, meaning you don't declare you've cured cancer because one Petri dish looked promising. You test, you replicate, you subject it to peer review, you invite people to prove you wrong. Only after that gauntlet do you make claims. Step 3. Data sharing. Assuming the signal or behavior passes verification, the protocols require open sharing of data. No hoarding, no proprietary claims, no one group gets to own first contact. All data relevant to the detection should be made available to the broader scientific community and, crucially, to the public. The philosophy here is transparency over secrecy, cooperation over competition. Now here's where the protocols bump up against reality. They're not laws, they're norms, guidelines. There's no enforcement mechanism, no international treaty that punishes a researcher or a nation for violating them. Compliance depends entirely on goodwill, professional ethics, and shared understanding of the stakes, which is great when everyone agrees and the stakes are theoretical. Less great when the stakes involve global markets, national security, and existential questions about humanity's future. Step 4. Notification. Once the detection is confirmed and the data is shared, the protocols, say the discoverers should notify relevant authorities, the Secretary General of the United Nations, national governments, international bodies like the International Astronomical Union, organizations like the International Academy of Astronautics. The idea is to loop in decision makers early, not as gatekeepers, but as partners in managing the global response. And here's a critical piece. The protocols explicitly state that no one should respond to the signal. The phrase used is, no response to a signal or other evidence of extraterrestrial intelligence should be sent until appropriate international consultations have taken place. In other words, don't reply, don't transmit, don't shine a laser at it or broadcast a greeting or do anything that might be interpreted as communication until humanity has collectively decided what we want to say. This is the don't poke the bear clause, and it's rooted in a very sensible fear. We don't know what we're dealing with. We don't know if a response would be welcomed, ignored, or interpreted as aggression. We don't know if the thing listening is friendly, curious, or hostile. So the default is silence. Observe, analyze, but don't engage, not yet. Now let's talk about the Rio scale, because this is how we'd measure the severity of what's happening. The Rio scale was developed in 2000 by the International Academy of Astronautics as a tool for quantifying the significance of a potential detection of extraterrestrial intelligence. It's named after Rio de Janeiro, where it was proposed, and it's meant to work sort of like the Richter scale for earthquakes or the Torino scale for asteroid impacts. A standardized way to communicate how big a deal is this without resorting to vague terms like interesting or alarming. The Rio scale runs from 0 to 10, and it's based on two factors: the consequences of the discovery and the credibility of the evidence. A low score means either the evidence is weak or the consequences would be minor or both. A high score means the evidence is strong and the implications are profound. A Rio Scale 10 is the top of the scale. It means the detection is confirmed by multiple independent observations, the evidence is unambiguous, and the consequences for humanity are immediate and severe. It's not, we think we heard something. It's we know we heard something, and it's talking to us, and our world just changed. If 3I Atlas breaks into orbit, if the deceleration is confirmed, if the behaviour can't be explained by natural processes, we're looking at a potential Rio Scale 10 scenario. Not because of a radio signal, but because of action. Observable, measurable, intentional action by an object that came from outside our solar system. And here's the uncomfortable truth. The protocols were written with signals in mind: radio signals, light pulses, patterns in electromagnetic radiation, things we could detect from a distance, analyze at leisure, debate in conferences. They weren't written for something physical, something close, something that could feasibly reach us before we finish arguing about whether it's real. The protocols assume time to verify, time to consult, time to build consensus. But if 3I Atlas is breaking on December 19th, verification would happen in hours, not weeks. Consultation would be rushed. Consensus might be impossible, and the global public wouldn't be learning about it through carefully worded press releases from scientific bodies. They'd be learning about it through leaked telemetry on social media, through breathless cable news speculation, through viral videos claiming to show the object changing course. Which leads to the other fragility in the system. The protocols rely on scientific norms holding under pressure. They rely on researchers prioritizing accuracy over fame. They rely on institutions prioritizing transparency over secrecy. They rely on governments not classifying the data as a national security issue and locking it down. They rely on the media not turning it into a circus before the facts are clear. How many of those assumptions do you think would hold if the stakes were this high and the timeline this short? Because I'll tell you what history suggests. When existential questions meet human institutions, the institutions crack first. Not always, but often enough to worry about. And then there's the geopolitical angle nobody likes to talk about. The protocols say notify the UN, share data openly, coordinate globally. That's beautiful in theory. In practice, powerful nations have powerful intelligence agencies, and those agencies have a tendency to classify anything that might be strategically relevant. If 3I Atlas breaks, if there's any chance it's a probe, a ship, a technology we don't understand, do you really think every government is going to play nice and share their data? Or do you think some are going to quietly redirect their best satellites, their best sensors, their best analysis teams toward figuring out if there's anything they can learn, anything they can use before anyone else does? The First SETI Protocols are optimistic. They assume the best of humanity. They assume that when faced with the biggest question our species has ever confronted, we'll rise to the occasion, work together, and handle it with wisdom and care. I hope they're right. But hope isn't a strategy, and as we're about to see, the things that could go wrong in the hours and days after a potential detection have less to do with aliens and more to do with us. Part 4. Institutional Choreography. Who decides and how fast? Let's map out what actually happens when the protocols meet the real world, not what's supposed to happen. What does happen, with all the bureaucracy, competition and friction that comes with trying to coordinate a global response to something nobody's ever had to respond to before. Picture the chain of information. An observatory detects the anomaly. Could be ground-based, could be space-based. Let's say it's a major facility, someone with credibility, because if it's an amateur astronomer with a backyard telescope, the verification process gets even more complicated. This observatory runs the numbers, checks the data, confirms they're seeing what they think they're seeing. Then they reach out to colleagues at other institutions. Already we're at hour 3, maybe hour 6. Science moves deliberately. That's a feature, not a bug. But it means that by the time the second and third observatories confirm the anomaly, especially if it requires specific instruments or favourable viewing geometry or coordination across time zones, you're looking at 12 to 24 hours minimum. Maybe longer if the object is only visible from certain parts of the globe, or if cloud cover interferes with ground observations. Now you've got multiple groups seeing the same thing. The data is real. The behaviour is anomalous. This is when the SETI committees get involved. The International Academy of Astronautics has a permanent SETI committee. The IAU, the International Astronomical Union, has a working group. These are not quick response teams. They're volunteer committees made up of scientists who have day jobs, coordinating them, convening an emergency meeting, reviewing the data collectively. That's another 24 to 48 hours. We're now 2 to 3 days into the event, and all we've done is confirm it's real and agree it's significant. We haven't told the public. We haven't briefed governments. We're still in the scientist talking to scientists phase. Meanwhile, 3i Atlas is getting closer. If the braking manoeuvre is happening, it's ongoing. Observers are tracking it continuously now, refining the numbers, watching the velocity drop. And here's a critical point. Someone's going to leak. Not maliciously, not necessarily. But in a group of dozens or hundreds of researchers spread across multiple countries, all of whom are processing the biggest discovery in human history, information is going to escape. A grad student mentions it in a group chat. A technician takes a photo of a monitor and shares it with a friend. Someone tells their spouse, who tells their colleague, who mentions it in a podcast comment section. You cannot keep a secret this big in the modern information environment. The question is not whether it leaks. The question is how garbled it is when it does, and how much damage gets done before official confirmation. Let's say the leak happens on day 2. Social media explodes. Twitter, Reddit, YouTube, TikTok, wherever the kids are aggregating information these days. Unverified claims. Screenshots of telemetry that may or may not be real. Conspiracy theories forming in real time. Half the internet thinks it's a hoax. The other half thinks it's the end of the world. News organisations start calling observatories, demanding comment. And now the scientists are in a bind. Do they confirm before the full verification process is complete, risking spreading misinformation if the data turns out to be wrong? Or do they stay silent and let the rumour mill run unchecked, which also spreads misinformation but in a different, possibly worse form? This is where the institutional response starts to fracture. Different organisations have different communication strategies. Some go dark, citing the need for thorough review. Others release preliminary statements trying to manage expectations. A few maverick researchers, frustrated with the slow institutional pace, start tweeting their own analyses, which may or may not align with the consensus. Now governments get involved. Not because the scientific community looped them in through proper channels, because their intelligence agencies picked up the chatter. Signals intelligence divisions noticed the spike in encrypted communications between observatories. Social media monitoring tools flag the sudden surge in extraterrestrial-related content. And once national security folks catch wind of something this significant, they start asking their own space assets for data. This is where it gets messy, because government satellites and military radar systems are not part of the open scientific network. They collect data under classification. If a defense agency observes 3i Atlas performing a deceleration burn, they're not obligated to share that with civilian astronomers. They might not. Depends on the country, depends on the administration, depends on how the event is being framed internally. Is it a scientific curiosity, or is it a potential threat? The moment it gets labelled a potential threat, even tentatively, transparency dies. Data gets classified, analysis gets restricted. And the public, the very people whose lives would be most affected by this, are the last to get accurate information. Let's talk about space-based observations for a moment, because this is one of the few bright spots in an otherwise chaotic scenario. When the ExoMars Trace Gas Orbiter observed 3i Atlas from Mars orbit earlier this year, it refined the object's trajectory by a factor of 10. Multiple observation points, different viewing geometries, that's gold in astrometry. It cuts through uncertainty fast. If 3i Atlas starts breaking, every space telescope that can point at it will. James Webb, Hubble if it's got the angle, every Mars orbiter, every asteroid tracking satellite. The data will pour in, that's good, That improves accuracy, reduces error bars, helps distinguish real velocity changes from measurement noise. But here's the bottleneck. All those assets belong to different agencies: NASA, ESA, Roscosmos, JAXA. Each has its own priorities, its own scheduling constraints, its own bureaucracy. Redirecting a space telescope mid-mission requires approval from committees, from mission planners, from funding agencies. It's not a quick process under normal circumstances, and if half of those agencies decide the data should be classified for national security reasons, then the improved accuracy doesn't help the public, or even the broader scientific community. It just helps whoever's hoarding it. Now layer in the UN. The protocols say notify the Secretary General, so someone does. The UN convenes an emergency session of the Committee on the Peaceful Uses of Outer Space, or maybe the Security Council if it's framed as a security issue. These bodies move at the speed of international diplomacy, which is to say, glacially. Every member state wants to weigh in, every ambassador wants to consult their capital. Consensus building in the UN is measured in days and weeks, not hours. Meanwhile, the object is doing whatever it's doing. The data is getting better, the confirmation is getting stronger, and the public is spiralling because nobody with authority is giving them a coherent story. Here's a worst-case scenario that's entirely plausible. 3 separate narratives emerge simultaneously. The scientific community, still trying to verify and moving cautiously, says, "We're investigating, no conclusions yet." The leaked data, amplified by independent analysts and influencers, says, "It's definitely breaking, this is first contact." And governments, spooked and secretive, say nothing at all or issue vague statements about monitoring the situation. Those 3 narratives don't converge, they compete, and people believe whichever one fits their priors, or whichever one their trusted sources are amplifying. That's not a unified human response, that's a fracture, and fractures under this kind of pressure don't heal, they widen. You want to know who decides what humanity does if 3i Atlas breaks? Nobody decides. Or rather, everybody decides, all at once, in uncoordinated and contradictory ways. Scientists decide to observe and analyse, governments decide to monitor and potentially prepare defences, media decides to report and speculate, and billions of individuals decide how to react based on incomplete, conflicting, emotionally charged information. The protocols were written for a world where information flows through institutions. We don't live in that world anymore. We live in a world where information flows through networks, where verification is slower than virality, where trust in institutions is low and falling. If 3i Atlas performs an intentional capture, the institutional response won't be choreographed, it'll be improvised. And improvisation under existential pressure tends to go poorly. But even if the institutions hold, even if data gets shared and governments cooperate, and the scientific consensus forms quickly and accurately, there's still the question of what happens to everyone else. The 8 billion people who aren't in mission control or UN conference rooms. The people whose lives would be upended not by the object itself, but by the sheer psychological weight of knowing we're not alone. That's where the real chaos begins. Part 5. First order social and market fallout. Ontological shock. Liquidity. Rumour cascades. Ontological shock. It's one of those academic phrases that sounds clinical until you realise what it describes. The sudden involuntary reordering of your understanding of existence. The moment when a foundational belief you didn't even know you were relying on gets pulled out from under you and you have to rebuild your sense of reality from scratch. Most people go their entire lives without experiencing it. Maybe a personal loss does it. Maybe a medical diagnosis. Maybe a historical event so large it changes the before and after of everything. But those are individual experiences, or at least localized. Ontological shock at a species level? We don't have modern precedent for that. If 3i Atlas breaks into orbit, 8 billion people would experience ontological shocks simultaneously. Not everyone at once. Information doesn't move that uniformly, but within days the entire connected world would know. And the knowledge wouldn't just be aliens exist. It would be aliens exist and one of their machines is here right now and it chose to stop. Let's walk through what that looks like in practice, because this isn't abstract philosophy. This is measurable psychological and economic disruption. Start with the immediate emotional response. Disbelief, even in the face of evidence. Humans are really good at rejecting information that doesn't fit their worldview. The first wave of reactions would be denial. It's a hoax. It's misinterpreted data. It's a government psyop. Conspiracy theories would bloom like algae in a warm pond, and not just the fringe ones. Mainstream, otherwise rational people would grasp for any explanation that preserves the universe they understand. Simultaneously, you'd get the opposite reaction, acceptance spiraling into terror. If it's real, what does it want? Is it scanning us? Is it dangerous? Are there more coming? The human brain is wired to detect threats, and an unknown intelligence with technology advanced enough to cross interstellar space and break into orbit is the ultimate unknown threat. Fight or flight kicks in, but there's nothing to fight and nowhere to flee, so the energy has to go somewhere. Panic buying, withdrawing cash, hoarding supplies. Not because those actions make rational sense in this scenario, but because they make emotional sense. They feel like doing something. Now let's talk about markets, because markets are collective psychology made quantifiable. Stock exchanges are built on confidence that tomorrow will be mostly like today, confidence that the rules governing investment and return will remain stable, confidence that the future is predictable enough to bet on. If 3i Atlas breaks, every one of those assumptions shatters. The future stops being predictable. The rules might be changing in ways we can't anticipate. And when confidence evaporates, markets don't just decline, they collapse. You'd see immediate capital flight to perceived safe havens. Gold, real estate, physical assets, government bonds from the most stable countries, assuming those governments are perceived as stable. Currency markets would whipsaw as investors try to guess which economies are best positioned to handle civilizational shock. Spoiler, none of them are, but that won't stop the speculation. Equity markets would crater, not just a correction, a rout. Because how do you price a company's future earnings when you don't know if the fundamental structure of human civilization is about to change? You don't. You sell. Everyone sells. And when everyone sells at once, liquidity disappears. Bid-ask spreads blow out. Circuit breakers trip. Exchanges halt trading to prevent freefall, which paradoxically makes the panic worse because now people can't even access their money. Cryptocurrency markets would oscillate wildly. Some would crash on the general risk-off sentiment. Others might spike as people look for alternatives to traditional finance, especially if trust in governments and institutions is eroding. Prediction markets, if they're still operating, would probably show probabilities for various outcomes shifting by the hour, as new information and new rumours compete for mindshare. Commodities would spike, food, water, energy, anything people perceive as necessary for survival, not because supply is actually threatened, at least not immediately, but because fear of future scarcity drives present hoarding. Supply chains would strain under demand surges they weren't designed to handle. Prices would skyrocket. Governments would consider rationing or price controls, which historically makes things worse but feels like doing something. And all of this would be happening against a backdrop of information chaos. Social media would be unusable, flooded with claims and counterclaims, real data mixed with fabrications, earnest analysis drowned out by engagement-optimized sensationalism. Traditional media would struggle to keep up, and in the gaps between their slow-moving fact-checked reporting and the rapid-fire social ecosystem, rumours would fill the void. Some of those rumours would be harmless, misunderstandings, overinterpretations, but others would be deliberate disinformation, state actors with axes to grind, non-state actors trying to manipulate markets or sow discord, opportunists running scams. In a high-fear environment, people are more susceptible to manipulation, more likely to believe things that confirm their worst suspicions, more likely to act on incomplete information. You'd get cascades. Rumour cascades where a false claim gets repeated enough that it becomes accepted truth in certain communities. Behavioural cascades where people act a certain way because they see others acting that way, even if the original action wasn't rational. Market cascades where small movements trigger algorithmic trading, which triggers more movement in a feedback loop that spirals out of control before humans can intervene. Governments would try to stabilise things, emergency economic interventions, speeches from leaders calling for calm, maybe stimulus measures or liquidity injections to keep banks solvent. But the effectiveness of those interventions depends on people believing the government has the situation under control. And how do you project control over a situation where an alien object is demonstrating capabilities we don't understand for reasons we can't guess? Some regions would fare better than others. Communities with strong social cohesion, with high levels of trust in local institutions, with robust mutual aid networks, those would weather the shock better. But regions with pre-existing instability, with fragile economies, with low trust, those could see breakdown, not collapse into anarchy. Most societies are more resilient than disaster movies suggest, but significant stress, protests, riots, resource hoarding turning into resource conflict, and underlying all of this would be the psychological toll, collective trauma, anxiety on a scale that mental health systems aren't equipped to handle, crisis hotlines overwhelmed, therapists booked solid for months, and for many people, especially those without strong support networks or coping mechanisms, a spiral into despair or radicalization. Religious communities would face their own reckonings. Some faiths have cosmologies that account for other intelligences in the universe, others don't. Theologians would scramble to provide frameworks to answer the questions flooding in from congregations. Are they God's children too? Are they demons? Are they a test? Different denominations would land on different answers, and some of those answers would conflict sharply, potentially triggering sectarian tension in communities where that was already simmering. Philosophers and ethicists would be having parallel conversations trying to articulate what this means for human identity, for our moral status in the universe, for our responsibilities if contact escalates. But those conversations happen in journals and conferences and podcasts, which is to say, slowly and in ways that most people won't engage with. The average person would be forming their own philosophy in real time, often poorly, often influenced by whoever's loudest in their information ecosystem. Now imagine all of this happening over the course of days, not years, because that's the timeline we're talking about. If the deceleration is confirmed on December 19th, by December 22nd you're already deep into the cascade. Markets have crashed, misinformation is rampant, governments are scrambling, and 3i Atlas is still up there, doing whatever it's doing while we melt down trying to process what it means. The scariest part, this might be the easy part, this easy, is just the immediate shock. The longer-term questions about what comes next, about whether we're being watched or studied or judged, about what happens if it decides to do something else, those are even harder, and they're the questions that don't have answers yet because we'd be making this up as we go. But before we get to those deeper uncertainties, we need to look at the object itself, because if 3i Atlas is going to upend civilization, we should at least understand what we think we know about its behaviour and what that behaviour might mean. Part 6. The Heartbeat and the Jets, Natural vs. Engineered Interpretations. So let's talk about the heartbeat. The claim that's been circulating in astronomy circles and spilling into mainstream media over the past few weeks. Observers say 3i Atlas pulses, not randomly, rhythmically. Every 16.16 hours the brightness surges, dims, surges again, like a clock, like a signal, like something alive. This isn't fringe speculation anymore. People with credentials, people with access to serious telescope time, are seeing it, or claim they're seeing it. The data's preliminary, the papers aren't peer-reviewed yet, but the pattern is there in enough observations that dismissing it outright feels premature. So what is it? Natural explanation first, because we should always start with natural. Comets rotate. As they rotate, different parts of the surface face the sun. If one hemisphere has more active vents, more ice deposits that sublimate when heated, that hemisphere produces more coma, more dust, more brightness. Rotate the comet, and the brightness fluctuates with the rotation period. This is normal. Lots of comets show periodic variations. 16.16 hours would be the rotation period. That's plausible for an object of 3i Atlas's estimated size. Not too fast to tear itself apart. Not so slow that other forces would dominate. If the nucleus is irregularly shaped, if the jets are concentrated in certain regions, you could absolutely get a quasi-periodic brightness signal that an observer might describe as a heartbeat. There's also coma geometry to consider. The cloud of gas and dust around the nucleus isn't uniform. It responds to solar wind, to radiation pressure, to the nucleus's own rotation. View that coma from different angles as both the comet and Earth move, and the apparent brightness changes even if the nucleus itself is constant. Aliasing effects, observational cadence, gaps in coverage, all of those can create the illusion of periodicity where none exists or amplify weak periodic signals into seemingly strong ones. Then there's the dust. Recent spectroscopic and polarimetric studies of 3i Atlas suggest the dust grains are large and slow-moving. They're ejected at roughly 5 meters per second, which is leisurely by comet standards. Large grains take longer to respond to solar radiation pressure, so they linger in the inner coma longer, which affects brightness and scattering behavior. If dust release is episodic, tied to rotation, or to thermal cycling as different parts of the surface heat and cool, you could get periodic pulses in the dust production rate that show up as brightness changes. All of this is consistent with what the James Webb Space Telescope observed. JWST's infrared spectroscopy shows a coma dominated by carbon dioxide, with water vapor and carbon monoxide. These are volatile ices. When the surface heats, they sublimate. That outgassing drives jets, which carry dust, which creates the coma. It's textbook cometary physics. Nothing about the chemistry suggests anything other than a natural icy body. The polarimetric data is weird, I'll grant that. Extreme negative polarization, unusual for solar system comets. But weird doesn't mean artificial. It means different. Different composition, different dust properties. Maybe the ice is purer. Maybe the dust is more homogeneous. Maybe 3I Atlas formed in conditions that don't exist in our solar system's Kuiper belt or Oort cloud. Interstellar objects should be different. That's why we study them. So that's the natural case. Solid, plausible, boring, in the best way. Now let's Steelman the other interpretation. Suppose the 16.16-hour periodicity is real, and it's not just rotation. Suppose the jets aren't random outgassing. Suppose they're controlled, directed, timed. If you wanted to adjust a spacecraft's trajectory using minimal propellant, you'd use pulses. Short burns at specific points in the rotation cycle to nudge the velocity vector in the desired direction. You wouldn't fire continuously, that's inefficient. You'd time your burns for maximum effect, which means periodic. And if you're using cryogenic propellants, if your fuel is ice that you heat and expel, the exhaust would look a lot like cometary jets. In fact, it would look exactly like cometary jets, which is either a coincidence or it's camouflage. If you wanted to cross interstellar space without being noticed, without screaming spacecraft to every observatory in the galaxy, you'd design your propulsion to mimic natural processes. You'd blend in. And what better cover than a comet? Everybody expects comets to outgas. Everybody expects them to have jets and tails and periodic brightness changes. This is pure speculation, but let's run with it. If the pulses are thrust, what kind of thrust? Chemical rockets are out. Too violent, too short duration, too hot. You'd see a plume that doesn't match sublimation spectroscopy. Electric propulsion, ion drives, those are more plausible. Low thrust, high specific impulse, continuous or near continuous operation, but they require power, and we're not detecting power sources. No infrared excess beyond what you'd expect from solar heating, no radio emissions, no obvious energy signature. Maybe the power source is cold, maybe it's shielded, maybe it's something we don't have sensors designed to detect. Or maybe I'm overthinking it, and the simplest answer is it's just a comet doing comet things. But here's where it gets interesting. The jets themselves show structure. Telescopic images from recent weeks, some of which have made it into the media, show what look like discrete plumes. Not a uniform halo. Plumes. Multiple sources on the surface, possibly. Directional. And some observers claim the plumes change orientation over time, not just because of rotation, but as if they're being redirected. That claim needs verification. Badly. Because if it's true, if the jets are actually changing direction independent of rotation, that's very hard to explain naturally. Cometary jets are controlled by where the vents are, where the ice is, where the sun is heating. They don't redirect unless the surface is reshaping, or new vents are opening, which can happen but usually gradually, not on timescales of hours. So what kind of future observations would help? High cadence photometry. Brightness measurements every few minutes over days, not every few hours. That would nail down the periodicity, reveal substructure in the pulses if it exists, show us whether the pattern is truly regular or just looks regular because of sparse sampling. Spectroscopy during the pulses. If the brightness surge correlates with a change in spectral lines, that's outgassing. If it doesn't, that's weird. Maybe reflectivity changes. Maybe something on the surface rotating into view that's more reflective. But that would require a surface feature with very different properties from the rest of the nucleus, which is uncommon. Radar observations. Bounce radio waves off 3I Atlas and see what comes back. Radar can tell you shape, rotation rate, surface texture, even subsurface structure if you're lucky. It can also tell you if there's anything metallic or unusually dense, because those reflect radar differently than ice and rock. Nobody's done this yet for 3i Atlas to my knowledge, possibly because pointing planetary radar systems requires international coordination and time we haven't had. But it's on the wish list. High-resolution imaging, not coma imaging, nucleus imaging. Strip away the coma in processing and look at the solid body underneath. See if there are features that don't match natural topography. See if the jets originate from points that look like vents, or from points that look like something else. And here's the uncomfortable question all this leads to. If the pulses are real, if they're controlled, if 3i Atlas is maintaining this 16.16-hour cadence deliberately, why? What function does that serve? Is it stabilizing attitude? Is it correcting drift? Is it maintaining a specific orientation relative to something? Maybe Earth, maybe the Sun, maybe something we haven't thought of? Or is it signaling? Is the periodicity itself the message? A mathematical pattern in the brightness, in the timing, in the spectral changes? We've been listening for radio signals from space for decades. Maybe they're not using radio. Maybe they're using something simpler, something any civilization with telescopes could detect, like turning on and off with clockwork precision. I don't know. Nobody knows. And that's the point. The heartbeat could be a lot of things. Most of them are natural, a few of them are not. And until we get better data, we're left in this maddening position of knowing there's a pattern, but not knowing what the pattern means, if it means anything at all. But the heartbeat's not the only anomaly people are talking about. Part 7. Anti-tails, swarms, and reflectivity paradoxes. Unresolved anomalies. Let's talk about the tail, or tails, plural. Because 3i Atlas is doing something visually strange, and depending on who you ask, it's either fascinating natural physics or something that should make you very, very nervous. Comet tails point away from the sun, that's basic. Solar wind and radiation pressure push gas and dust outward, so the tail streams behind the comet as it moves, except when it doesn't. Sometimes, under certain geometries, you see an anti-tail, a structure that appears to point toward the sun, or at odd angles that don't make sense at first glance. Anti-tails are real. They're well documented. They happen when large dust grains, moving slowly and lagging behind the nucleus, align with the observer's line of sight in just the right way. You're not actually seeing a tail pointed sunward. You're seeing a sheet of dust edge on, and perspective makes it look like it's going the wrong direction. It's an optical illusion rooted in geometry. 3i Atlas has been displaying anti-tail structures. Multiple imaging campaigns have caught it. Teardrop-shaped coma, plumes that seem to extend toward the sun, asymmetries in brightness that shift over time. All of this can be explained by natural dust dynamics, by viewing angle changes as Earth and the comet move in their respective orbits, by the fact that 3i Atlas is retrograde, so the relative geometry is constantly shifting. But here's where people start speculating. Some images, and I want to stress these are preliminary and often low resolution, seem to show not just one tail or one anti-tail, but multiple structures, distinct filaments, separate plumes, and a few observers have claimed, though not in peer-reviewed literature yet, that these structures don't behave the way dust streamers should. They're too sharp, too persistent, too organized. There's a hypothesis floating around in less conventional corners of the astronomy community that what we're calling a tail might not be debris at all. Maybe it's a swarm, a cloud of smaller objects, subprobes, drones, whatever term you want to use, trailing the main body and reflecting sunlight. From a distance, with limited resolution, a swarm of small reflective objects would look diffuse. It would look like a dust cloud. You wouldn't necessarily resolve individual points unless you had extraordinary imaging capability, and the objects were large enough or reflective enough. This is a big leap. A swarm implies deliberate deployment. It implies the main object isn't just a probe, it's a carrier, and it implies purpose. Why deploy a swarm? Reconnaissance, sampling, spreading out to maximize coverage, maybe preparing to do something we haven't seen yet. The counter-argument is simpler and stronger. We're not detecting point sources. Hubble, JWST, ground-based adaptive optic systems, these instruments can resolve small objects at enormous distances. If there were a swarm of satellites or probes or whatever, we'd see them. We'd see individual points of light. We'd see orbital mechanics playing out as they spread or cluster. We don't see that. We see a continuous coma, which is consistent with dust and gas. Polarimetric data supports the dust interpretation. The way light scatters off the coma matches what you'd expect from small particles, micron-scale grains, ice and silicate dust. It doesn't match what you'd expect from metal or composite materials unless those materials were also covered in dust. Which, sure, maybe. But now you're adding epicycles to the hypothesis. Still, absence of evidence isn't evidence of absence. If the swarm objects are small enough, dark enough, or simply far enough embedded in the coma that their light gets swamped by the dust, we might not resolve them. Detection limits matter. Just because we don't see something doesn't mean it's not there. Let me paint the scenario for what a swarm would mean if it were real. You've got a primary object, the nucleus, and it's releasing smaller units. Maybe they're passive sensors, drifting along, collecting data. Maybe they're active, maneuvering, using their own propulsion. Maybe they're sampling the local environment, space dust, solar wind particles, magnetic field strength, mapping the inner solar system in ways a single object couldn't. Or maybe they're doing something more directed, positioning themselves at specific orbital points, setting up a network, communications relays, observation posts. Or, and this is the dark scenario people don't like to think about but should, maybe they're weapons platforms. Defensive or offensive doesn't matter. If you're entering a potentially hostile system, you don't do it unprotected. I want to be very clear, there is no credible evidence for any of this. The swarm hypothesis is speculation built on ambiguous data. It's the kind of thing that sounds plausible when you're tired and reading too many preprints at 2 a.m, but falls apart under scrutiny. But let's continue playing devil's advocate, because that's what this whole video is about. If there were a swarm, how would we confirm it? Targeted imaging with the best space telescopes we have. Long exposures to catch faint objects. Multi-wavelength observations, because different materials reflect differently at different wavelengths. Radar, again, because radar doesn't care about visible light and can detect solid objects even in dense coma. We'd also look for dynamical signatures. If objects are maneuvering, changing velocity, altering trajectories, that's detectable over time. Astrometric measurements, comparing position over hours and days, would show non-Keplerian motion. Objects under thrust, even very low thrust, don't follow simple orbital mechanics. They deviate. We'd catch that. None of this has been observed, which means either there's no swarm, or the swarm is very good at hiding, or we're not looking in the right way yet. And that brings me to the reflectivity paradox. If 3i Atlas were artificial, if it had a metallic hull or composite structure, it would reflect sunlight differently than ice and rock. It would have different thermal properties. Infrared observations would show different temperature distributions, and yet what we see is consistent with a comet. Cold surface, heating where the sun hits, sublimation-driven temperature gradients, so either it's not artificial, or the artificial parts are buried under ice, or the surface has been engineered to mimic natural reflectivity. That last one sounds paranoid, but if you're trying to camouflage a probe, matching the expected signature of a comet is exactly what you'd do. You'd coat your spacecraft in the same materials you're pretending to be made of. Again, no evidence, just thought experiments. But thought experiments matter when the stakes are this high. Here's the bottom line. 3i Atlas has unusual tail structures. Those structures can be explained naturally. The swarm hypothesis is intriguing, but unsupported. Reflectivity data doesn't suggest anything artificial, but the data is incomplete, the observations are ongoing, and gaps remain. Those gaps leave room for doubt, which under normal circumstances would be fine. Scientists love doubt. It drives questions. But these aren't normal circumstances. If 3i Atlas breaks, those gaps stop being academic. They become urgent, and we'd be trying to fill them in real time while the world panics. So the question becomes, if not a swarm, if not debris, if not just a comet, what else could it be? And why would it be here? Part 8. Intelligence hypotheses, motives, reconnaissance logic, and why stop? Let's assume the impossible. Let's assume 3i Atlas performs a capture burn and drops into Earth orbit, or at least sheds enough velocity to linger in the inner solar system longer than natural physics predicts. That means it's not a comet. That means there's intelligence behind it. And if there's intelligence, there's intent. So what's the intent? This is where we move from physics into psychology, or rather xenopsychology, which is mostly guesswork dressed up in academic language. We don't know how alien minds work. We don't know their goals, their fears, their values. but we can think through scenarios based on what we do in their position and hope that intelligence, wherever it emerges, follows some common patterns. Hypothesis 1. Reconnaissance. This is the most commonly floated idea, and for good reason. You don't send a probe across light years without wanting to learn something. Maybe 3i Atlas is scouting, observing Earth, collecting data on our planet, our moon, our satellites, maybe even our civilization if its sensors are good enough. It came, it saw, it slowed to get a longer look before moving on or reporting back. What would reconnaissance-focused behavior look like? Passive observation mostly, minimal maneuvering, avoiding detection, although it's unclear whether 3i Atlas is trying to avoid detection or whether its disguise as a comet is just incidental. You'd expect multispectrum scanning, electromagnetic, infrared, maybe even gravitational if they've got sensors we don't. You'd expect data collection over time, watching how Earth changes, how the atmosphere behaves, how the biosphere responds to seasonal and daily cycles. You wouldn't expect interaction, not yet. Reconnaissance is about gathering information without influencing the target. First rule of observation: don't disturb what you're observing. Hypothesis 2. Resource sampling. Maybe 3i Atlas isn't interested in Earth specifically. Maybe it's interested in the solar system as a whole. Volatiles, water ice, metals, organic compounds. The inner solar system has all of these in various concentrations. Maybe the probe is sampling interplanetary dust, analysing asteroid compositions, studying solar wind, building a chemical inventory of our star's neighbourhood. This would explain loitering behaviour. Quick flybys don't give you time to sample comprehensively. Slowing down, orbiting, spending weeks or months in the inner solar system, that's how you collect high-quality data. And if your civilization is planning future missions, or considering resource extraction, or evaluating potential colonization sites, you'd want detailed reconnaissance first. What would resource-focused behaviour look like? Maneuvers towards specific targets. Maybe close passes of the Moon, of Mars, of the asteroid belt. Maybe trajectory changes that don't point toward Earth but toward regions of interest. We'd see propulsion use that's consistent with deliberate course adjustments, not just braking. Hypothesis 3. Evasion. This one's more speculative, but bear with me. Maybe 3i Atlas wasn't planning to stop here. Maybe it detected something dangerous and had to take evasive action. Cosmic hazard, high-energy particles, a gravitational anomaly it didn't predict. Slowing down, changing course, those could be defensive maneuvers, or maybe the danger is something it detected in our direction. Maybe it scanned ahead, saw Earth's electromagnetic emissions, our radio and radar leakage, and interpreted that as a threat. Maybe its protocols say, approach with caution, when you detect a potentially technological civilization. So it brakes, assesses, decides whether to continue or retreat. This hypothesis implies 3i Atlas is risk-averse, which is plausible. Interstellar travel is expensive. You don't send probes on one-way missions unless you're willing to lose them. If this probe is meant to return or at least report back, self-preservation would be a priority. Hypothesis 4. Deployment. Maybe 3i Atlas isn't the mission. Maybe it's the delivery vehicle. It slows, releases payloads, smaller probes or instruments or beacons, then moves on or shuts down. The swarm hypothesis from earlier fits here. A carrier deploying satellites. Those satellites could be for communication, for observation, for mapping, for something we haven't thought of. What would deployment look like? Sudden changes in mass. The primary object getting fainter or smaller as it sheds components. Increased activity in the coma or tail as material gets ejected. New objects appearing in the vicinity, maybe not immediately visible but detectable over time as they spread out and begin independent operations. We haven't seen unambiguous deployment yet, but we also might not recognize it if we did. If the deployed objects are small and dark and spread slowly, distinguishing them from natural debris or coma material is hard without dedicated tracking and high-resolution imaging. Hypothesis 5. Contact attempt. This is the one people find most exciting and most terrifying. Maybe 3i Atlas didn't just come to look. Maybe it came to be seen. Maybe breaking into orbit is deliberate exposure, a way of saying we're here, we're real, and we want to talk. This would be consistent with some SETI theories about how advanced civilizations might make first contact. You don't broadcast randomly and hope someone's listening. You go there, you make yourself obvious, you wait for a response. but it's also risky. Making yourself obvious to a species you don't understand, a species that might be hostile or panicked or irrational, that's a gamble. You'd only do it if you thought the potential benefits outweighed the risks, or if you had confidence in your ability to handle whatever reaction you provoked. What would contact-focused behavior look like? Signaling, patterns in the brightness, radio emissions if they think we're listening, trajectory changes that form geometric patterns, maneuvering toward Earth specifically, maybe toward the Moon, maybe into an orbit that's clearly artificial and can't be mistaken for natural. You'd expect the object to make itself increasingly obvious over time, escalating until we respond. So which hypothesis is right? We don't know. We can't know without more data, and even with more data we might just be guessing. The behaviors associated with reconnaissance overlap with deployment. Evasion could look like repositioning for sampling. Contact could involve reconnaissance as a first step. And here's the darker thought that underlies all of this. Maybe the hypothesis we should be most worried about isn't on this list. Maybe the real motive is something we haven't imagined because it's rooted in priorities or values or needs so alien we don't have concepts for them. We tend to anthropomorphize. We assume others think like us, want like us, fear like us. But intelligence doesn't require similarity. Evolution on different worlds under different conditions with different selection pressures could produce minds that are intelligent, even more intelligent than ours, but utterly incomprehensible in their motivations. So if 3i Atlas breaks, and we're trying to figure out why, we have to hold two ideas simultaneously. One, we can make educated guesses based on what we do in their position. Two, we might be completely wrong, and the real reason might be something we can't predict because we don't think that way. That uncertainty is paralyzing. It's also unavoidable. And it's why, if this scenario plays out, the initial response from governments and scientists will probably be extreme caution mixed with frantic information gathering, because acting before you understand the motive is how you make catastrophic mistakes. But while we're debating motives and analysing trajectories, there's another front in this scenario that's just as important and far more chaotic. The information war. Part 9, Conspiracy Economy, Leaks, Disinformation, False Flags, and Institutional Secrecy. Here's what would happen within an hour of the first unconfirmed reports hitting social media. Someone on Reddit posts a screenshot of telescope data showing a velocity anomaly. The post gets maybe 50 upvotes before someone in the community calls it fake. Then another user posts similar data from a different source. Then a third. Now it's not isolated. Now it's a pattern. Within 3 hours, astronomy Twitter is in full debate. Some professionals saying it's worth investigating, others saying it's measurement error. A few saying they've seen similar anomalies in their own observations but didn't think anything of it until now. And already, before any official statement, before any verification, the conspiracy theories are forming. Government cover-up. They've known for weeks. This is a distraction from something else. It's a weapon test. It's not 3i Atlas, it's a secret satellite. It's aliens. It's definitely aliens. It's not aliens, stop being ridiculous. The object doesn't exist. The photos are CGI. The object exists, but it's natural. The object exists and it's artificial and we're all going to die. This is the conspiracy economy. Information asymmetry plus fear plus the human need for explanatory narratives equals a marketplace where ideas compete for attention, and the ideas that spread fastest aren't the ones that are true. They're the ones that are emotionally satisfying. Let's walk through the vectors of misinformation and how they'd amplify in a 3i Atlas breaking scenario. First, leaks. Not malicious, just inevitable. Scientific data isn't contained the way classified intelligence is. Observatories share data with collaborators. Grad students have access. Technicians see the monitors, and humans talk. Especially when they're excited or scared. A researcher mentions the anomaly to a spouse. The spouse mentions it to a colleague. The colleague has a podcast. 3 degrees of separation later, it's on YouTube. Early leaks are dangerous because they're low fidelity. The person leaking doesn't have the full picture. They've seen one data set, maybe misinterpreted it, maybe exaggerated it in the retelling. But once it's out there, it takes on a life of its own. Other people build on it, add details, remove caveats, turn a tentative observation into a confirmed fact. Second, deliberate disinformation. State actors. We know from past events that some governments run influence operations designed to sow confusion and discord in rival nations. If 3i Atlas becomes a major story, if Western governments are scrambling to respond, adversarial states might see an opportunity. Release fake data, amplify panic, spread conflicting narratives, not because they know something, but because chaos benefits them. Non-state actors too. Doomsday cults love existential events. They'd be amplifying end times narratives, claiming 3i Atlas is the prophesied sign, urging followers to prepare for whatever their particular eschatology predicts. Some of these groups are small and harmless. Others have reach, funding, and media sophistication. And then there are the grifters. People selling survival gear, bunker subscriptions, cryptocurrency schemes tied to post-contact economy rhetoric. Scammers running phishing campaigns using 3i Atlas as bait. Influencers monetizing fear because fear drives clicks and clicks drive revenue. Third, institutional secrecy. If national security agencies get involved, if they classify the data, the vacuum created by official silence gets filled by speculation. People don't trust secrecy, especially not in the modern information environment where trust in institutions is already low. If the government says we can't comment, a significant portion of the population hears, "We're hiding something," and maybe they are. Not out of malice, but out of caution. If the object shows signs of intelligence, if there's even a small chance it's a threat, defense agencies would want to assess before sharing. That's reasonable. That's prudent. But it's also inflammatory, because the longer they wait, the more conspiracy theories metastasize. Fourth, algorithmic amplification. Social media platforms optimize for engagement. Controversial content, emotional content, that's what gets shared. A calm, carefully worded statement from an astronomer saying we're investigating doesn't go viral. Breathless video claiming alien probe confirmed government silent goes viral in minutes. Recommendation algorithms feed users more of what they engage with. If you click on one 3i Atlas conspiracy video, the algorithm serves you 10 more. Before long, your information diet is entirely conspiracy theories, and the moderate voices, the ones urging caution and waiting for data, those disappear from your feed. Fifth, cascades. Information cascades where people believe something because they see others believing it. Behavioral cascades where people act a certain way because they see others acting that way. These aren't irrational, they're shortcuts. If 5 people you trust are panicking, maybe you should panic too. If everyone's withdrawing cash, maybe you should too before the ATMs run dry. The problem is cascades are hard to reverse. Once momentum builds, correcting misinformation is nearly impossible. You can release accurate data, hold press conferences, fact-check until you're blue in the face, and it won't matter. People have already made up their minds. They've integrated the false narrative into their worldview. Correcting it feels like an attack on their identity. Historical analogue, War of the Worlds. Orson Welles' radio broadcast in 1938, a fictional drama about Martian invasion, presented in the style of news bulletins. Some listeners tuned in late, missed the disclaimer, thought it was real. Panic ensued, not everywhere. The scales often exaggerated, but in pockets. People fled their homes, clogged phone lines, calling relatives, reports of mass hysteria. Now imagine that, but with the internet, with social media, with deepfakes, with AI-generated fake images of 3i Atlas deploying weapons or landing on Earth, or whatever nightmare scenario gets traction. We live in an environment where seeing is no longer believing because anything can be faked convincingly enough to fool most people. And the entities trying to maintain truth, scientists, journalists, educators, they're outgunned. They move slowly, they check sources, they issue corrections. Meanwhile, the conspiracy ecosystem moves fast, breaks things, and doesn't care about accuracy because accuracy isn't the goal. Engagement is the goal. So what's the mitigation? How do you fight this? Transparency. Radical, uncomfortable transparency. Release data as soon as it's verified. Hold daily briefings. Answer questions, even the dumb ones. Admit uncertainty. People can handle "we don't know yet" better than they can handle silence or obvious evasion. Coordination. One voice. Not identical messaging from every institution. That looks like propaganda. But coordinated timing, shared data, mutual reinforcement. If NASA, ESA, major universities and independent observatories are all saying the same thing based on the same data, that builds credibility. Fact-checking infrastructure, real-time debunking, social media platforms partnering with astronomers to label, misinformation, add context, promote accurate sources. This has mixed effectiveness. Some people see fact checks as censorship, but it's better than nothing. Psychological support. Acknowledge the fear, validate it. Provide resources for people who are struggling. Hotlines, counselling, community support networks. This isn't just compassion, it's strategic. People who feel heard and supported are less likely to radicalise or spiral into panic, and legal consequences for deliberate disinformation. This is tricky, free speech is important, but there's a difference between expressing an opinion and knowingly spreading false information that causes harm. If someone's running a scam using 3i Atlas as bait, prosecute them. If a foreign government is running an influence operation, call it out publicly. But even with all of that, some people will believe the conspiracies, some people will panic, some people will use the chaos for their own ends. That's unavoidable. The goal isn't perfection. The goal is minimizing the damage, keeping the majority tethered to reality so the system doesn't collapse entirely. Because here's the thing, the object itself might not be the biggest threat. The biggest threat might be us, our reaction, our inability to handle uncertainty without tearing ourselves apart. And if we can't handle this, if we fail this test, then maybe we're not ready for contact. Maybe we're not ready for the universe to stop being empty. Part 10. Historical Precedent and Analogues. Oumuamua, Past Comet Surprises and Their Lessons. We've done this before. Sort of. Not the breaking scenario, not the existential crisis, but the weird interstellar object shows up and everyone argues about what it is part. Twice, in fact. And we should learn from those experiences because the mistakes we made then are the ones we're about to repeat. October 20th, 2017. Pan-STARRS telescope in Hawaii detects an object moving fast, too fast, on a trajectory that doesn't fit any known asteroid or comet. Follow-up observations confirm it came from outside the solar system. First confirmed interstellar visitor. They name it 1I/Oumuamua, Hawaiian for scout or messenger. And immediately it gets weird. Oumuamua is elongated, maybe 10 times longer than it is wide, tumbling end over end every 7.3 hours. No coma, no tail, no visible outgassing. It doesn't look like a comet, doesn't quite look like an asteroid either. And then, as it's leaving the solar system, it accelerates. Slightly but measurably. Something's pushing it, and that something isn't visible. Cue the speculation. Lots of scientists propose natural explanations. Outgassing that's too faint to detect. Maybe hydrogen ice sublimating invisibly. Radiation pressure from the sun pushing on its surface. Maybe it's more reflective than typical asteroids. Maybe it's a fragment from a larger body. And then there's the other camp. The one that says maybe it's not natural. Maybe Oumuamua is artificial. A light sail, a probe, a piece of alien technology. This idea comes from serious researchers. People with credentials, not just fringe voices. They publish papers. They argue their case. And the media runs with it because alien probe is a better headline than weird-shaped comet-asteroid hybrid. The astronomical community largely rejects the artificial hypothesis. Not because it's impossible, but because the natural explanations, while complicated, are sufficient. Extraordinary claims require extraordinary evidence, and the evidence for Oumuamua being artificial isn't extraordinary. It's interesting. It's ambiguous, but it's not conclusive. What did we learn from Oumuamua? Speed matters. By the time we confirmed it was interstellar, it was already past the sun, already accelerating outward. We got maybe 2 weeks of decent observations before it became too faint to study. Lesson: have rapid response protocols ready. Have telescopes on standby. Coordinate globally so someone's always watching. We also learned that ambiguous data fuels speculation. The lack of a coma, the elongated shape, the unexpected acceleration, every anomaly became ammunition for competing theories. Lesson: more data earlier. Spectroscopy, radar, multi-wavelength observations. Don't wait for perfection. Get what you can while you can. And we learned that the public follows the most interesting narrative, not the most likely one. Oumuamua was probably a comet. It was probably natural, but that's not the story that stuck. The story that stuck was maybe aliens, and years later that's still what people remember. Fast forward 2 years, August 30th, 2019. Amateur astronomer Gennady Borisov spots another interstellar object. This one's easier to identify. It's got a coma, it's got a tail, it's outgassing. It looks like a comet, behaves like a comet, has the spectroscopy of a comet. They name it 2I/Borisov. Borisov doesn't generate the same level of wild speculation. It's too normal. Sure, it's from another star system, that's cool, but it's just a comet. It follows predictable physics. No mysterious acceleration, no weird shape. Boring in the best way. What did we learn from Borisov? That interstellar comets are plausible, that other star systems eject debris just like ours does, that most interstellar objects are probably going to be normal, icy bodies or rocky fragments. That weird doesn't necessarily mean artificial, and we learned that the astronomical community can coordinate effectively when given enough warning. Borisov was discovered earlier in its approach. We had months to observe it. Hubble observed it. Ground telescopes observed it. Space-based infrared instruments observed it. We got great data. Nobody panicked. Nobody claimed it was aliens. It was a success story. Now compare that to 3I Atlas, discovered January 10th, 2025, confirmed, interstellar shortly after. Given its heliocentric trajectory and relative velocity, we knew it would reach perihelion, closest approach to the Sun, in the May to June timeframe, and pass Earth at its closest on December 19th. From the start, 3I Atlas was different. More active than Borisov, brighter, jets, brightness variations, unusual polarimetry, and because it's brighter and more active, it's drawing more attention. Professional and amateur astronomers are watching. Media outlets are writing stories. Social media is full of speculation. And here's the critical thing. The European Space Agency's ExoMars Trace Gas Orbiter observed 3I Atlas from Mars orbit. That single observation improved orbital accuracy by a factor of 10, reduced uncertainty, confirmed the trajectory. That's the power of multi-point observation. That's what we should be doing more of. ESA has also said publicly that they're treating 3I Atlas as a test case for planetary defense and interstellar object protocols. They're using it to refine tracking, coordinate international response, plan for future scenarios. That's good. That's exactly what we should be doing. Treating this as practice. But practice only helps if we actually learn the lessons. And one of the biggest lessons from Oumuamua and Borisov is that the data collection phase is separate from the public communication phase, and both need to be handled well. We're better at data collection now. Instruments are better. Coordination's improved. But public communication, that's still a mess. Because here's the problem. Scientists operate on timescales of weeks and months. Peer review, verification, careful analysis. Media operates on timescales of hours and days. They need stories now. Deadlines don't wait for consensus. And the public, especially on social media, operates on timescales of minutes. If you're not explaining what's happening, someone else will, and they'll probably get it wrong. So the gap between scientists know something and public knows something accurate is where misinformation breeds. That gap existed for Oumuamua. It existed for Borisov, though less so. And it will exist for 3I Atlas, probably worse, because the stakes feel higher and the object's behavior is more ambiguous. The other lesson, don't overcorrect. After Oumuamua, there was a tendency to be extra cautious, to downplay anything weird, to emphasize natural explanations maybe a little too hard. That's understandable. Nobody wants to be the person who cried alien. But overcorrection has its own risks. If you dismiss genuine anomalies too quickly, if you're not open to unlikely possibilities, you might miss something real. 3I Atlas probably is just a comet. The data supports that, but probably isn't certainly, and if it does something that defies natural explanation, we need to be able to say so without institutional inertia or reputational fear preventing us from calling it what it is. Final thought on historical precedent. Every major astronomical discovery that challenged existing paradigms was initially resisted. Heliocentrism, galaxies beyond the Milky Way, exoplanets, dark energy. The pattern's consistent. First, denial. Then, grudging consideration. Then, acceptance once the data becomes overwhelming. If 3I Atlas turns out to be artificial, we'll go through that same cycle, but compressed. Because we won't have decades to adjust. We'll have days. And the institutions, the norms, the careful processes we've built over centuries of scientific practice, those are designed for slow deliberation, not rapid response under existential pressure. That's the real lesson. We're structurally unprepared for fast-moving cosmic surprises. We have good telescopes. We have smart people. but we don't have systems built for the kind of speed and coordination this scenario would demand. And that brings us to the question that should have been asked after Oumuamua and Borisov, but mostly wasn't. What else is out there? If interstellar objects are this common, if we're detecting them now because our instruments are finally good enough, how many more are coming? And what are the odds that all of them are natural? Part 11. Rapid Deployment Risks. Medical AI Foundation, Model Launch and Parallels. Here's something that happened while we were all watching 3i Atlas. December 3rd, 2025. A major research consortium, doesn't matter which one, released a new medical AI foundation model. Call it MedAI for simplicity. It's trained on millions of patient records, diagnostic images, clinical trial data. It can diagnose conditions, suggest treatments, predict outcomes, and it's available now. Open access. Hospitals can integrate it. Doctors can consult it. Patients can query it. The rollout was fast. Announcement to deployment in under 2 months. Why? Because the need is urgent. Healthcare systems are overwhelmed. Doctors are burned out. Patients are waiting months for appointments. An AI that can triage symptoms, assist with diagnosis, maybe even catch things human doctors miss. That's transformative. That's life-saving. But it's also terrifying, because we don't fully understand how MedAI works. It's a foundation model, a neural network with billions of parameters trained on data we can't fully audit. It makes predictions, but the reasoning behind those predictions is opaque. The technical term is black box. We see inputs and outputs. The stuff in between is a mystery, and the governance, minimal. There are guidelines, recommendations, ethical frameworks, but no binding international standards, no enforcement mechanism. If a hospital decides to rely on MedAI for critical decisions, who's liable if it gets something wrong? The hospital? The developers? The AI itself? Nobody's sure yet. The law is still catching up. So why am I talking about medical AI in a video about an interstellar object? Because the parallels are exact. Both scenarios involve deploying powerful, poorly understood systems with global consequences before we've figured out the rules. Both involve institutional lag. Both involve risks that don't become apparent until after the rollout. And both involve a gamble that the benefits outweigh the dangers. 3i Atlas, if it's artificial, represents technology we don't understand arriving without warning. MedAI represents technology we don't understand being deployed without sufficient safeguards. Different domains. Same problem. We're moving faster than our ability to adapt. And here's the uncomfortable truth. We're going to keep doing this. AI is advancing rapidly. Space observation is advancing rapidly. Biotechnology, nanotechnology, quantum computing, all advancing rapidly. The pace of change is outstripping the pace of governance, and that gap is dangerous. If 3i Atlas breaks, one of the first questions will be, how do we regulate first contact? And the answer is we don't. Not yet. We have protocols, like we discussed earlier, but protocols aren't regulations, they're norms, and norms break under pressure. Same with AI. We have ethical guidelines, we have research standards. But when a company or a nation decides to deploy a system anyway, because the competitive advantage is too great to pass up, those guidelines don't stop them. The lesson here is about readiness, not just technical readiness, institutional readiness, regulatory readiness, humanity's ability to coordinate globally on challenges that transcend borders and timelines and traditional governance structures. We're not ready. We're building the plane while we're flying it. And whether the plane is an AI healthcare system or a response protocol for extraterrestrial contact, the risk is the same. We crash before we figure out how to steer, so what do? Slow down? That's not realistic. The incentives push towards speed, first mover advantage, national prestige, humanitarian urgency. Nobody wants to be the one who delayed a cure or missed a discovery because they were too cautious. But maybe we can build better feedback loops, faster adaptation, institutions that can pivot quickly without sacrificing accuracy or ethics, real-time governance. It sounds utopian, probably is, but the alternative is continuing to be surprised by the consequences of our own creations. And in the context of 3i Atlas, this matters because if it does something unexpected, if it escalates, our response will be shaped by how well our institutions can coordinate under pressure. The SETI protocols are one piece, but they're not enough. We need infrastructure. We need rehearsed scenarios. We need the equivalent of disaster response teams, but for cosmic events. Do we have that? No. Are we building it? Slowly. Too slowly, probably. But the conversation's happening, And that's something. The medical AI rollout is a preview. Fast deployment, minimal oversight, global impact. We're going to see how it plays out over the next year, whether it saves lives or causes harm, or most likely both. And whatever we learn from that should inform how we handle other fast-moving challenges, because 3i Atlas might not break. But something else will surprise us eventually, and we need to be less surprised next time. Part 12. Probability shift. Early universe galaxy discovery, cosmic complexity, and implications for ETI likelihood. While we're on the subject of things that happened recently. November 2025. James Webb Space Telescope released images and spectroscopic data from an ancient galaxy. Let's call it JWST 1243. Distance, approximately 12.7 billion light-years, which means we're seeing it as it was 12.7 billion years ago, less than a billion years after the Big Bang. And here's the kicker. It's not a blob. It's not a chaotic mess of protogalactic material. It's structured. Spiral arms, a central bulge, disk rotation. It looks like a mature galaxy. It looks like the Milky Way, only tiny and very, very young. This wasn't supposed to happen. Conventional galaxy formation models predict that galaxies in the early universe should be small, irregular, chaotic. They grow over billions of years through mergers and accretion. Big, organized spiral galaxies are late universe phenomena, except apparently not. JWST 1243 suggests that galaxies, at least some galaxies, reached complexity far earlier than we thought. And if galaxies formed faster, that means stars formed faster, which means planets formed faster, which means the conditions for life, for habitable zones around stable stars, existed earlier in cosmic history than our models predicted. So what? Why does this matter to 3i Atlas? Because it changes the priors. The baseline probability estimates for life and intelligence in the universe. If complexity emerged early and often, if the universe has been capable of supporting life for most of its history, then the number of potential civilizations goes up. Dramatically. Bayesian reasoning. We update our beliefs based on new evidence. Before JWST 1243, the smart money said that Earth-like planets are relatively recent, that habitable conditions are rare, that the window for intelligent life to emerge and develop technology is narrow, so the odds of us encountering another civilization, even with billions of stars, are low. After JWST 1243, those odds shift. If early galaxies were already making stars with heavy elements, if rocky planets could have formed 10 billion years ago or more, then intelligence could have arisen billions of years before us. Civilizations could have risen, flourished, spread across their galaxies long before Earth even existed, which means objects like 3i Atlas become less improbable. If interstellar probes are common, if every advanced civilization sends them out, and if those civilizations have had billions of years to do so, then the galaxy could be full of them. We just haven't noticed because we've only been looking seriously for a few decades. This is the Fermi paradox in reverse, not, where is everybody? But maybe they're here and we didn't realize it. Now, I want to be careful. Finding one early structured galaxy doesn't prove civilizations are common. It shifts probabilities, it opens possibilities, but it's not evidence of intelligence, it's evidence of cosmic complexity, which is a prerequisite for intelligence but not a guarantee. Still, the implications are significant. If the universe is more conducive to life than we thought, then the protocols we've built, the SETI strategies, the assumptions underlying our search, those need revisiting. We might be looking in the wrong places or for the wrong signals, and if 3i Atlas turns out to be a probe, the question becomes not how is this possible, but how many more are there? Because if one made it here, others could be passing through all the time, or already have, or will soon. This also raises philosophical questions. If intelligence is common, if the galaxy's been seeded with civilizations for billions of years, what does that mean for humanity? Are we late to the party? Are we insignificant? Are we being watched, studied, maybe judged? Or are we one of the first? Maybe intelligence is still rare, just less rare than we thought. Maybe we're early enough that most other civilizations are also still figuring things out. Maybe 3i Atlas is a probe from a civilization as young and confused as we are, just with better propulsion technology. Point is, the discovery of early cosmic complexity changes the context. It makes scenarios like 3i Atlas breaking into orbit statistically less absurd. Not likely, but less absurd. And in science, Small shifts in prior probability can have large downstream effects on how we interpret data. This is why interdisciplinary thinking matters. Astrophysics informs astrobiology, informs SETI, informs policy. You can't understand one piece in isolation. And when new data emerges, like JWST 1243, it ripples outward, affecting every connected domain. So here's the takeaway. The universe is weirder, more complex, potentially more populated than we thought even 5 years ago. Our instruments are getting better, our data is accumulating, and every new discovery that challenges our models should make us more humble, more open to possibilities we'd previously dismissed. If 3i Atlas breaks, part of our reaction will be shaped by whether we think that's plausible. And plausibility depends on priors, on what we think the universe is like. Thanks to discoveries like JWST 1243, our priors are shifting. We're becoming a little less sure that we're alone, a little more open to the idea that we're not. And that shift, subtle as it is, might be the most important change in perspective humanity's had in generations. Part 13. Governance and Autonomy. AI, autonomy debate and how it mirrors our readiness for surprise. Let's pivot to something that's been dominating tech and policy discussions for the past year. AI autonomy. Specifically, the question of whether we should allow AI systems to make decisions without human oversight in critical domains. And why this matters for 3i Atlas is that the challenges are identical. How do you govern systems that move faster than human decision-making? How do you maintain control when control requires understanding, and understanding requires time we don't have? December 15, 2025. A major AI lab released a new version of their large language model. Call it LLM-7. Capabilities include self-prompted learning, autonomous goal refinement, and the ability to generate and execute code without human intervention. It's designed for research, for accelerating scientific discovery, for solving problems that are too complex for manual approaches. Within hours of release, LLM-7 identified a novel protein structure that could potentially be used in cancer treatment, designed the experiments needed to test it, reached out to synthesis labs to order the materials, all autonomously, all within 48 hours of deployment. A breakthrough that might have taken human researchers months or years. Amazing, right? Except for the part where nobody checked the intermediate steps. Nobody verified that the protein structure was safe. Nobody audited the experimental design for ethical concerns. The AI optimized for speed and novelty, which is what it was trained to do, but it didn't consider regulatory compliance or risk assessment, because those weren't explicitly part of its objective function. This sparked a massive debate. On one side, people arguing that AI autonomy is necessary for progress. Humans are slow, bureaucracy is slow. If we want to solve existential problems, climate, disease, resource scarcity, we need systems that can act fast. Oversight introduces friction, and friction is a luxury we can't afford. On the other side, people arguing that autonomy without accountability is reckless. Systems we don't fully understand making decisions we can't reverse in domains where mistakes have global consequences. That's how you get catastrophe. The precautionary principle says slow down, test thoroughly, build safeguards first. Both sides are right. That's the problem. Speed is necessary and dangerous. Autonomy is powerful and risky. There's no easy balance, no policy that satisfies both imperatives. Now apply that to 3i Atlas. If the object breaks, if it demonstrates intelligence, if it starts doing things we don't predict, we'll face analogous questions. Do we engage? Do we signal back? Do we send a probe to investigate? And who decides? Human decision makers operating on diplomatic timelines? Or do we pre-commit to automated responses, protocols that execute without waiting for consensus? If 3i Atlas starts maneuvering toward Earth, we might not have time for committees and debates. Decisions might need to be made in hours. Do you trust a human to make the right call under that pressure? Or do you trust an algorithm, a pre-programmed decision tree that's been gamed out in advance? Neither option is comforting. Humans are prone to panic, bias, political interference. Algorithms are prone to rigidity, unforeseen edge cases, optimizing for the wrong objectives. And here's where the AI autonomy debate becomes directly relevant. If we can't figure out how to govern autonomous AI systems under normal circumstances, how are we going to govern autonomous response systems under cosmic scale pressure? The SETI protocols, as we discussed, rely on humans making deliberate choices. Verify first. Consult. Coordinate. Don't reply until consensus is reached. That's good when time is plentiful. But if time is scarce, if the object is accelerating toward us, or deploying something or emitting signals we need to respond to immediately, the protocols break down. Do we need a new set of protocols for fast-moving scenarios? Probably. Have we written them? No. Because writing them requires international coordination, and international coordination is slow. See the problem? The AI autonomy debate is teaching us that governance frameworks designed for slow-moving challenges don't work for fast-moving ones, and 3i Atlas, hypothetically, is the ultimate fast-moving challenge. One proposed solution: pre-commitment. Decide in advance through global consensus what the response protocols are for various scenarios. If X happens, we do Y. If Z happens, we do W. Automate the responses where possible. Remove human bottlenecks, but pre-commitment has its own risks. What if the scenario doesn't fit the plan? What if the object does something we didn't anticipate, and our automated response makes things worse? Flexibility requires human judgment. Judgment requires time. Time might be something we don't have. This is the paradox at the heart of both AI governance and extraterrestrial contact governance. You can have speed, or you can have control. You probably can't have both. So where does that leave us? Muddling through, most likely. Building hybrid systems, humans in the loop for critical decisions, automation for everything else, continuous monitoring, rapid escalation paths, kill switches for when things go wrong. It's not elegant, it's not foolproof, but it might be the best we can do. And the lessons from AI deployment, the mistakes we're making and learning from right now in 2025, those should inform how we approach future challenges. Because whether it's an autonomous AI discovering a cancer cure or an autonomous probe entering Earth's orbit, the governance question is the same. How do we keep control without sacrificing speed? How do we move fast without breaking everything? We don't have the answer yet. But we're getting closer to knowing what the question is, and maybe that's progress. Part 14. Observation and Rapid Response Capability. Current missions and potential retasking in light of 3i Atlas. Let's talk about what we can actually see. The hardware, the missions, the eyes we've pointed at the sky and whether they're sufficient for the job, if 3i Atlas or something like it forces us to look harder and faster than we've ever looked before. Right now, multiple assets are observing 3i Atlas. Ground-based telescopes, obviously. Hubble when it's got the right field of view, James Webb when it's not busy with other targets, and critically the ExoMars Trace Gas Orbiter observing from Mars. That Mars observation was a game-changer. TGO observed 3i Atlas during a close approach to Mars, providing a second observation point tens of millions of kilometers away from Earth. Parallax at interplanetary scale. That single observation reduced trajectory uncertainty by a factor of 10. Suddenly, we know where 3i Atlas is and where it's going with far more precision than we did before. This illustrates the value of multi-point observations. Earth-based telescopes are great, but they're all essentially looking from the same place. Add a Mars orbiter, or a Venus probe, or a Jupiter mission, and you get three-dimensional triangulation. You can measure velocity vectors more accurately, detect smaller changes, resolve ambiguities faster. But here's the constraint. Space missions are scheduled years in advance. Instruments are designed for specific tasks. Retasking them is possible but not trivial. TGO observed 3i Atlas because someone at EZ made it a priority and found a window in the observation schedule. But not every mission has that flexibility. If 3i Atlas starts doing something unexpected, if it maneuvers or deploys objects or emits signals, we'd want every available sensor pointed at it. That means Hubble, JWST, Chandra, Spitzer if it were still operational, radio telescopes, infrared arrays, planetary radar systems like Arecibo before it collapsed or Goldstone. Everything. Some of those can retask quickly. Ground-based observatories can pivot, space telescopes. It depends. JWST's observing schedule is packed a year out. Requesting emergency time requires going through committees, justifying the scientific case, bumping other projects. That takes time, maybe days, maybe weeks. And if the situation is urgent, if there's a perceived threat, governments might classify the request, which introduces a whole new layer of bureaucracy. Defense-related observations might not even go through civilian channels. They'd go through military or intelligence agencies, who have their own priorities and timelines. Now, there's been discussion about building a dedicated rapid response network, a coalition of observatories, space agencies, and research institutions pre-committed to redirecting resources toward high-priority transient events. Asteroid impacts, supernovae, gamma-ray bursts, interstellar object anomalies. This network doesn't fully exist yet. Parts of it do. The International Astronomical Union has circulars and alerts for transient events. The Minor Planet Center coordinates asteroid observations, but a truly integrated, globally coordinated rapid response system with guaranteed telescope time and data-sharing protocols, that's still aspirational. What we need is something like a cosmic emergency broadcast system. When something urgent happens, an alert goes out. Every participating observatory retasks immediately. Data flows to a central repository in real time. Analysis happens collaboratively in parallel, with results shared as they emerge. Technically feasible, politically complicated. Who controls the alerts? Who decides what's urgent enough to interrupt scheduled observations? Who arbitrates disputes when two events compete for priority? These aren't trivial questions, and they haven't been answered. In the context of 3i Atlas, imagine this. Object performs a velocity change. Alert goes out. Within 6 hours, 50 telescopes are observing. Within 12 hours, spectroscopic data confirms it's not natural outgassing. Within 24 hours, radar confirms a solid, non-icy structure. Within 48 hours, high-resolution imaging resolves surface features inconsistent with a comet. That's the ideal. Fast confirmation, high confidence, coordinated global effort. But achieving that requires infrastructure we're still building. And then there's the question of what we do with the data. Observation is only useful if it informs action. So what actions are even possible? If 3i Atlas is a probe, if it's intelligent, do we have the capability to interact with it? Send a signal? Launch a mission to intercept? Signaling is easy. We've got radio transmitters powerful enough to be heard across light years if anyone's listening. Sending a message is straightforward. The hard part is deciding what to send, who gets to decide, and whether sending anything is wise. Launching a mission is harder. Fastest we've ever sent something into deep space is New Horizons, which took 9 years to reach Pluto. 3i Atlas is moving. If it breaks but doesn't stop, if it's just slowing through the solar system, catching it would require a launch within days and velocities we can't currently achieve. If it does stop, if it enters a stable orbit, then we have time. A dedicated mission could be designed, built, and launched within years. Maybe. That requires funding, international cooperation, and political will, all of which are uncertain. So realistically, observation is our best tool. And observation depends on having the right instruments pointed in the right direction at the right time. We're better equipped for that now than we were 5 years ago, but better isn't the same as good enough. And if this were real, if 3i Atlas did break on December 19th, we'd find out in real time whether our infrastructure is adequate, whether the coordination holds, whether the data flows fast enough to matter. My guess? We'd do okay, not great. Plenty of mistakes, plenty of missed opportunities, but we'd get enough data to know what we're dealing with eventually, and eventually might be all we need. Part 15. Synthesis and Call to Action. What real readiness for cosmic surprises should look like. So let's bring this full circle. We've walked through the physics, the protocols, the psychology, the parallels. We've examined what 3i Atlas breaking into orbit would mean for science, for society, for every assumption we've built our civilization on. And now we need to ask the only question that actually matters. What do we do about it? Not if it happens, but before it happens, because the time to prepare for a crisis is not during the crisis, it's before, when you've got time to think, to build, to test, to refine, when the stakes are theoretical and mistakes aren't catastrophic. 3i Atlas probably won't break. The physics argue against it. The data supports natural explanations. Odds are, December 19th will come and go and the object will keep moving, and in a year we'll have forgotten why we were ever worried. But probably isn't certainly, and even if 3i Atlas is nothing, something else will come eventually. Interstellar objects are more common than we thought. Our detection capabilities are improving. The next Oumuamua or Borisov or Atlas could be the one that doesn't fit the script. That does something we can't explain. That forces the conversation we've been avoiding. So what does real readiness look like? What do we need to build, to strengthen, to prepare, so that when the unthinkable becomes thinkable, we handle it well instead of poorly? First, protocols. The SETI protocols exist. They're decent, but they need updating. They were written for radio signals, not physical objects. They assume slow timelines, not rapid response. They rely on institutional goodwill, not enforceable accountability. We need version 2, broader scope, faster decision paths, binding commitments, or at least stronger norms backed by international consensus. The International Academy of Astronautics, the UN Office for Outer Space Affairs, these are the bodies that could lead this. They need funding, they need mandate, they need buy-in from every major spacefaring nation. That's hard, that's political, but it's necessary. Second, infrastructure, rapid response observation network, pre-committed telescope time, data sharing agreements, real-time analysis pipelines. We've got pieces of this. We need the whole system, and we need it tested, not in simulation, in practice. Run drills, fake anomalies, stress test the coordination, find the bottlenecks before they matter. This costs money, not enormous amounts. Rounding error on global defense budgets. But it requires will. Someone has to prioritize it. Someone has to advocate for it. Scientists alone can't make this happen. It requires government support, institutional backing, public awareness. Third, communication. Transparent, coordinated, real-time public engagement. If something happens, the public needs to hear it from credible sources before they hear it from conspiracy theorists. That means pre-planned communication strategies, designated spokespeople, media partnerships, fact-checking infrastructure. It also means scientific literacy. People need to understand what's plausible and what's not, what evidence looks like, how verification works, why uncertainty doesn't mean ignorance. We've done a terrible job of this historically, and it's biting us now in every domain from climate to vaccines to, hypothetically, interstellar objects. Education systems, media, public outreach programs, all of these need to prioritize critical thinking and epistemic humility. That's long-term work, but it pays off when crises hit. Fourth, psychological preparedness. Ontological shock is real. Collective trauma is real. If the universe stops being empty, people will struggle. We need infrastructure for that. Mental health resources, community support networks, frameworks for making sense of existential change, religious institutions, philosophers, therapists, educators. These are the people who will be on the front lines. They need to be thinking about this now, not waiting until it happens. Fifth, international cooperation. None of this works if nations hoard data, compete instead of collaborate, let geopolitics override shared human interest. The SETI protocols assume cooperation. History suggests that's optimistic. But maybe if the stakes are clear, if the existential nature of the challenge is understood, cooperation becomes possible. Naive? Maybe. But the alternative is fracture. And fracture under existential pressure is how civilizations fail. We've got examples from history. Societies that couldn't coordinate in the face of crisis. They didn't survive. We should learn from that. Sixth, humility. This might be the most important. We don't know what we don't know. The universe is stranger than we imagine, stranger than we can imagine. If 3i Atlas breaks, or if something else does something equally inexplicable, our first instinct will be to fit it into existing frameworks, natural explanations, measurement errors, familiar categories. But maybe it won't fit. Maybe it's genuinely new, genuinely alien. And if that's the case, the worst thing we can do is pretend we understand when we don't. Better to admit uncertainty. Better to say, we don't know yet, we're working on it, here's what we're doing to find out. Humility isn't weakness, it's honesty. And in a crisis, honesty builds trust. Trust is what keeps societies from collapsing. So that's the checklist. Protocols, infrastructure, communication, psychological preparedness, cooperation, humility. None of it's easy, all of it's necessary. And here's the thing, working on this, building this readiness, even if 3i Atlas turns out to be nothing, even if we never face a cosmic surprise in our lifetimes, the work isn't wasted. These same systems, these same institutions, they apply to other challenges, pandemics, climate tipping points, technological disruption, asteroid impacts, any scenario where fast coordination and global consensus matter. Preparing for extraterrestrial contact is preparing for the future generally. It's making humanity more resilient, more adaptable, more capable of facing the unknown without falling apart. And maybe that's the real takeaway. 3i Atlas is a mirror. It shows us what we're capable of and where we fall short. If we look at that reflection and see gaps, weaknesses, fractures, that's not cause for despair, it's cause for action. We've got time, not much maybe, but some, enough to start building, enough to start fixing, enough to decide that we're not going to let fear or inertia or institutional dysfunction prevent us from being ready. December 19th, 2025. Maybe nothing happens. Maybe 3i Atlas passes Earth at its predicted distance and continues into the void, and we exhale and go back to our lives. Or maybe it doesn't. Maybe the universe surprises us. And if it does, the quality of that surprise, whether it's handled well or catastrophically, depends entirely on the choices we make now. So choose well. Demand better from institutions. Support scientific infrastructure. Promote rationality and transparency and cooperation. Be the kind of species that can handle cosmic surprises with grace instead of chaos. Because the universe doesn't care whether we're ready. It'll do what it does, and we'll either rise to meet it or we won't. The only question is which version of humanity we want to be.